Hi, everyone, and welcome to the ACSM Metabolic Equation lab. In this lab, we'll be covering how to use various predictive equations for different activities to say what sort of energy expenditure those activities will have, plus a few other variables that contribute to those. I think to start things off, covering what ACSM stands for is the American College of Sports Medicine. I think identifying that is going to add to some clarity as we move forward through these. And essentially, they're a regulating body of exercise physiology and exercise science based out of the States, but they have come up with a series of equations that we'll learn about today. So, kind of have some fun titles for this as we go through, just to make things a bit more interesting, I guess, and have a bit fun, because this is a bit math heavy, and for some that might not consider themselves math experts, it might seem a little intimidating or a little worrying at first, but my reassurance is that if you dedicate a little bit of time to learning the process of these equations, they're great. They're not that bad, really. And I believe that again, if you work through these tutorials and put in a bit of time, everyone in class should be able to handle these pretty good. So yeah. First up in the lecture, we're going to cover, I said, no need for Professor Trelawney. If you remember Harry Potter, she was the seer, the person that predicted futures through the crystal ball and tea leaves and stuff like that. She's a very fun character in that story. A little bit of an oddball, which is excellent for stories like that. And really what we'll just kind of get into there is how to measure or predict energy expenditure and how that happens, and dive into that and realize that it's not magic. It's pretty just straightforward, basic science based off of chemistry and biology primarily, and you'll see how some physics and thermodynamics work into that as well. Then we'll move from that into expressing different forms of energy expenditure. So there's a bunch of units and different forms of expression for energy expenditure that we have, that we can use. Then we'll get into what's the deal with all of these equations. Why would you ever use these? What is the usefulness? Why are you learning this, essentially? And hopefully that will, by the end of it, help you understand a bit more lay of the land, or lay of the equations, and what the different numbers mean. And I think pulling a bit of a Quentin Tarantino and setting up how this is going to end for you, and then working back to that, is going to be helpful here. So when you're looking at these equations, and any equations really, when it comes to the sciences, is every value has a meaning. So every letter that doesn't have a specific number is there for a variable, and that means something as far as how it relates to all the other numbers and variables in that equation. Whether it's something that's squared or multiplied or added, there's math functions that those relate to, but it tells you the type of relationship that each of these variables have between each other, and sometimes gives a little bit of an indication of what the really important variables are. So that being said, it'll lead to a greater understanding not just how to calculate these equations and do math and answer the questions on your quizzes and exams. It's more about understanding the relationship that each of these values have with each other, and how that gets set up in the equation, and how that explains quite beautifully how you can predict metabolic expenditure, energy expenditure. Okay, so that's not a setup for a lab lecture. I don't know what is. Okay, so we'll dive into the one of the main topics in understanding how we can go about predicting metabolic or energy expenditure is something called indirect calorimetry. Okay, and ultimately we're going to be following the O2. Now, without getting too far ahead quite yet, I want you to think back to the lab that you just did, and with the resting metabolic rate, or think about resting metabolic rate, and what you measure generally with a metabolic cart is the difference of carbon dioxide and oxygen in expired air. So again, it's how much oxygen typically is getting utilized and in what way, and how much energy that can predict. And as you know, you can also predict find an indication of what sort of energy is used as well to fuel that. So here again, we're going to be looking at indirect calorimetry to be an indication of how we can find our answers for energy expenditure. And it's done in a slightly different way than measuring directly the gas exchange. Okay, so again, we might even need to take a step back from last lab and reassess and reevaluate what is energy. So energy really is just the capacity to do work. Okay, that sounds kind of vague and ambiguous. What do you mean work? Capacity to do work. What is this? So it's really just, again, some conceptual nuance of something that can make something happen. That's even a more deconstructed version of that. So in regards to our body, getting a bit more specific now, ATP, so the energy currency of our bodies, that's essentially what allows us to do work. And if you recall from the last lab as well, that it's that third phosphate that gets attached to ADP, or adenosine diphosphate, di meaning two. So adenosine diphosphate becomes adenosine tri, so 3 phosphates. And when that third phosphate gets pulled away through its chemical bonds, it gets pulled away and essentially frees up energy. And that free energy, it's stored chemical energy that becomes usable energy when that chemical bond gets broken. So you free some energy to do work. We typically, when we're talking about energy in the body, we talk about calories. So we have food calories, which, again, familiar from the last lab, but even just life, you see calorie listings on the side of food, and it's fairly common knowledge that when you want to lose weight, you need to expend calories. So calories, again, is a form of energy, and we typically think of it as a way that our bodies burn, right? They burn calories. They utilize this energy, which is true, but the a more specific definition of calories is looking at actually how the unit is constructed as far as a baseline. So calories is 1 kilocalorie is essentially the amount of heat energy that comes from the breaking of chemical bonds, typically in the body, but or food, and it raises that heat energy from that chemical bond that gets broken and is released increases the temperature of 1 liter of water. So you can think of like a liter of milk, 1 degree centigrade. So just kind of wrap your head around that for a second. So again, it's energy, and the work when we're determining its baseline for a calorie is heat. So the way they do this with food, your foods, and how they come up with the nutritional information is they actually have a little calorimeter that they more or less just take, let's say, a sugar cube, because that will definitely ignite. They take the sugar cube, put it in this little thing, and they ignite it. They get a little spark, lights it on fire, and the sugar burns. And so however much heat that puts off will heat this enclosed container of water around this thing with a thermometer in it. And when you see a increase in temperature, that has a direct correlation to how many calories the food has. And that's what they do in testing sites. But obviously we don't light our food on fire within us. We get our energy from ATP. But more specifically, again, if you think back to last lab, this equation where oxygen equals energy. So it's oxygen and our food essentially can combine to give us energy and carbon dioxide and heat as a byproduct, okay? And so just reviewing that equation again now in a slightly new context as we move forward. When we go through aerobic respiration or cellular respiration at an aerobic level, we can correlate. We know fairly finitely, if we have X number of oxygen coming in based off of our RER, we're gonna have, or what sort of fuel is being used, we have X number of ATP or X number of energy being produced. So we get a pretty good correlation between the two, and we'll see how that plays out a little bit more detailed moving forward. So again, knowing how much oxygen or predicting how much oxygen is consumed allows us to predict how much energy has been produced. And there's a lot here, so I always like to warn students and people in general, whenever you see a big graph or something come up, an illustration, just hit the pause button, kind of back up from it all, go through it step by step, and figure out what it's saying. So let's do that together. I'll take a step back and we'll link what we were just saying about how you can look at oxygen and get a very good concept of how much energy is expended given how much oxygen is used, right? So again, this same equation written in a slightly different format that you've been seeing all along. So nutrition, or your nutrients or food plus oxygen, goes into carbon dioxide, water, and work. And work internally and externally, we've already mentioned heat, so that would be a bit of an external version of it. But we'll get into that in a bit. Okay. The main thing I want you to do is wheel back towards the start and look at oxygen. So these equations, we'll even go back a bit more. So last lab we were looking at, how much carbon dioxide was on the other side of the equation. So when you measured your expired breath, you breathed out into the metabolic cart, and what that told you in comparison to atmospheric air was how much oxygen did you turn into carbon dioxide. More or less, it was taking what was known at the start of the equation, comparing it on the back end, and seeing what that difference was. So that's what our last lab with the metabolic cart was looking at. And so again, that's an indirect measure, indirect calorimetry. If you want direct calorimetry for metabolism, it's a crazy looking machine. It's essentially a small closet or a room that's a tank, and the entire room is double walled, and in those walls you have water in it. Okay. Or essentially it's double walled, so heat energy can't get in or out. And neither can any unaccounted for air. So they actually have like an in gas comes into the room and an out vent that then gets scrubbed by some salts, which is what they do on the space shuttle. So scrubbed by some salts and kind of goes back into the room, refreshed but contained. And the key to all of this with the person in the room is there's usually copper piping, but there's some sort of piping with water in it. And with that water, you measure the temperature change. So if the person's just sitting there at a desk, breathing, resting, you can measure their resting metabolic rate by how much their body heat changes the temperature on the water, right? Remember back, what's a calorie or a kilocalorie? 1 kilocalorie increases the water temperature of 1 liter of water 1 degree centigrade. Okay, so that's essentially what it measures. But you get in this, like, it looks like you're in a submarine of some sort. Everything's very controlled because you can't have any energy or air or anything entering or escaping the system. So you can imagine these are really expensive. So the better alternative is to do something that's indirect. And so again, your metabolic cart is using the carbon dioxide typically on the other end of your expired air and comparing that to atmospheric. For the predictive equations today, here, right now, where we're at, it uses oxygen through indirect calorimetry. Okay, so just seeing how that can link up, we can follow this flow chart to see where all of the energy and all the components are being accounted for. So when again, oxygen is indirect calorimetry, CO2 indirect, but work, how do we figure this work out? So work is the capacity to do something. So you need energy for work, right? And this can happen internally or externally. Now in our bodies, that's done with ATP. So internally, typically when our cells have work done or do work at a cellular level, they'll give off heat. And again, it's from those chemical structures changing. But some of what that ATP energy goes to is, for easier concept, is like mechanical work. So turning the cranks on a bike, moving your limbs through space and time, or while you're running, or throwing a ball or something. So that's external work. So you change that energy at that cellular level into work, physical work, mechanical work that moves other things in space and time. Okay. So, we have these two forms, right? And it's not perfectly like that. Like, we are imperfect machines. And what I mean by that is whenever you're talking about the efficiency of a machine or something, there's always some loss of energy to other factors, and it's typically heat. And heat can come from friction or inefficiencies in general, but like a car, for example, is not a very efficient machine. Human bodies are on par to that, relatively speaking. There's much more efficient machines. And so we lose a lot of our energy from ATP through heat. We're just inefficient that way. So, and you can think about that when you start working or carrying heavy bags up and down stairs, and you start getting warm, right? So that's what's causing it, right? So even though we have external work happening, some of that produces heat through inefficiency, aside from the inefficiency and the heat generated from ATP converting to ADP as well. Okay, and ultimately you can measure both, right? You can measure, say, the work done on a bike by turning the crank with something called a power meter, and it will tell you how much work is physically being done or mechanically being done on the bike, as well as measuring how much heat you give off. Or in this case, you can look at CO2 or O2 indirectly, okay? So again, a few different ways that you can measure and account for all of the energy, all of the capacity to do work within the fundamental production of energy in our bodies, which is food and oxygen, into CO2, water, and work, ATP. Okay. There's a lot to digest there, so to speak. So yeah, feel free to go back, kind of take a look at it, at the flow chart, and just walk through it yourself again. But the big take-home message with all of this is there's indirect and direct calorimetry, and the next main point to take home is for indirect calorimetry. Last day we're looking at CO2 really as kind of the main source of figuring out how much of this equation is being used, so how much carbon dioxide is being produced. On the equations today, a lot of it is fundamentally focused around how much oxygen is used. Okay. So with the volume of oxygen, there's different ways you can express that and then convert it through unit conversions and different concepts that we'll see to understand how much oxygen is used, and that can tell us different information. So for example, when you're looking at volume of oxygen, again, you're looking for something that's typically in liters or milliliters. Okay, you're thinking of a volume of space. So again, you can think of the milk jugs or different containers again that you might have with food at home that deals with volume. Okay, measuring cups, etc. And while you can express it in absolute, so for example, the volume of oxygen in a milk jug is 4 liters, in a 4-liter milk jug, right? And so if you're thinking about volume of oxygen that the lungs can produce, typically it's expressed as a rate. They're usually always in some form of a rate of O2. So, 4 liters per minute, right? And so that's helpful when you're trying to say or figure out for some reason maybe the total amount of oxygen someone would need. For example, maybe diving, right? If you're scuba diving and you have a finite amount of oxygen you can bring with you, if you're trying to plan it out specifically, especially if you're trying to get certified for very deep water dives, Arctic or cold water dives, etc., you really have to calculate quite carefully your energy expenditure based off of yourself and your lung capacity and how many tanks you need to bring with you. So an absolute volume based off of how much you consume a minute, this would be helpful. Usually in exercise physiology, kinesiology, etc., when you're measuring VO2, volume of oxygen, you want to look at it relatively speaking for the person. As many of you kind of came across last week with resting metabolic rates, a large component of what drives our metabolism, our metabolic rate, our energy expenditure in general has to do with our body weight. So again, making something relative based off of someone's body weight is really important. This actually becomes even more important when you want to compare between body types, but also sports. Typically, that's where it can be really useful. So, for example, we'll make up some numbers, but hopefully this will help illustrate. So, the absolute amount of oxygen, say that a huge, large shot putter, just a large person, a couple hundred, 250 pounds or something like that, 6 foot whatever, their absolute volume of oxygen that they can produce and utilize is massive. They need it because they have so many cells in their body that are active. It'll be quite high. Whereas let's say a very short, petite marathon runner, their absolute VO2 might be quite low. Their body weight's only, let's say, 120 pounds or something, so significantly less. They have way less cells in their bodies and don't need to produce that much absolute volume of oxygen for their activity. But if you're to look at relative volume of oxygen use, in particular, if we think now VO2 max, so the maximum amount of oxygen your lungs can exchange to create energy, you take that absolute number and you divide it by their body weight. So all of a sudden now you have this shot putter who weighs 250, but their output, relatively speaking, to that body weight is quite small. Like it's once divided by their kilos, the amount of milliliters or liters of oxygen they can exchange isn't that much. Whereas the marathoner, their max VO2, because of their larger capacity for cardiovascular activity, is going to be much, much greater now, because they have way less body weight to divide that original number of. So again, just as an example, if the absolute VO or absolute O2 of the shot putter is 100, the marathoner is 100, but weighs much less. Again, relatively speaking, they have a better cardiovascular capacity to do work, right? So that has to do directly with volume of oxygen, absolutely and relatively. Again, they technically both are rates because it's per minute, which again, you could figure out per hour, how, multiply by 60, per day, per whatever. Or over 5 minutes, how much is this? Relatively speaking, it's multiplied by 5. So, but when you're talking about rate of O2 for energy, you can have kcals per minute, and that's another valid way of expressing energy expenditure when you're looking at these. Generally speaking, the ACSM equations, when you get to the unit for volume of oxygen, or VO2, it'll always be relative, and that's just the way they've standardized their equations. So you won't need to worry necessarily if it's in liters or kcals per minute or whatever. You might need to convert from that or from relative to one of those, but yeah. If otherwise stated, it's always going to be milliliters per kilogram per minute. Now, there's this funny thing called MET, and it's called metabolic equivalent. And more or less what it is a way to gauge on a scale, a relative scale, how much work something is, say physical activity. And it's based around the concept that for every 1 MET, that's 3.5 milliliters per kilogram per minute. Okay, sorry about the slide there. That should be a slash, not a period. So why is this? What is this all about? Why is this important? Well, really, what you're looking at when you look at 3.5 milliliters per kilogram per minute is the standard or average or equivalent of everyone at rest. So if you're just resting, doing nothing, sitting, laying down, resting, you're gonna have a metabolic equivalent of about 3.5 on standard. So, and again, if you look at the rate, it's 1 kilocalorie per kilogram per hour. Okay, that's the same as saying 1 MET. So 1 MET equals both of those. How does this help us? Well, when you start talking about different activities, you can essentially relate them to how many times more than rest they are, how much more metabolically active they are than at rest. So again, resting is 1 MET. Yoga typically is about 1.2, maybe 1.4. I think that'd be pushing it a little bit. Swimming at different intensities can be 3 METs, 5 METs, 10 METs. And again, all that's saying is that it's 3, 5, and 10 times more metabolically demanding than if you're at rest. So it's kind of a cool way to just conceptualize how demanding a certain activity is at a certain intensity. Okay, and they have charts that you can look at. How many METs is playing baseball on average? How many METs is cycling slowly? How many METs is walking? I think it's again similar to yoga, or just slightly above it. So yeah, so again, useful. And again, thinking back, what is the whole point of all of this? Well, we're trying to figure out energy expenditure of different physical activities. At the end of the day, that's ultimately what the ACSM equations were set up for. But they have a few more uses too. Okay, so METs is just one more set of units that we can use to express a similar concept. So the ACSM equations, what do they all mean? What is the deal with all of these equations, and what use are they? Well, I already alluded to one of the main ones, okay? And again, ultimately, I jumped ahead here to kind of the second point, but ultimately, there are different ways to prescribe and figure out different components of physical activity, okay? The first one is, again, through that indirect calorimetry, is you can estimate very easily, wherever you happen to be, how much VO2 or how much oxygen is exchanged without a metabolic cart. You can be at home, you can be in the gym, in the clinic, in wherever. So it's a very cost-effective way that you can relatively well predict energy expenditure. And there's some caveats to that, but we'll get to that in a second, okay? So no need for, and they are pretty expensive, a metabolic cart like you saw in the lab, last lab. The other thing that we typically use this for is determining work rate and energy expenditure, okay? So if you can think conceptually like in maybe a bit more of a fitness setting or a lab where you need to figure out how much energy someone is going to expend at a certain pace or work rate. So for example, on the treadmill, how fast do I need to set a treadmill for somebody to expend 100 calories in 5 minutes? You could use these to figure that out. Or what if you wanted to figure out how to expend 500 calories during a run? What would you need to set the treadmill? What if you're running outside? How could you figure that out? When you're talking about weight management and weight loss, for every pound of weight, or every pound of weight that you need to lose, you need to expend 3,500 kilocalories in a deficit. So ultimately, when you're trying to generate that deficit through nutrition and proper nutrition and exercise, if you're trying to offset a certain amount of food consumed for a day, or trying to generate, typically it's about a 200 calorie deficit a day. How can you do that through exercise? Well, figure that out. What exercise do you want to do? ACSM has some equations for walking, running, stepping upstairs, cycling, and I think those are the main ones. They have an arm cycle as well, but we won't be using that one. You could calculate it out. Okay, at what intensity do I need to do how much work on what device to expend 200 calories, right? Weight loss and weight management is a little more complex for that, but that's the numbers aspect. Okay, so that's why we would use the equations, but with these equations, as you've noticed with the resting metabolic rate equations, the body fat percentage equations, all of these carry certain assumptions and therefore certain sources of errors or parameters where they're ideal and other parameters where they're less ideal. Okay, so if we look here at these equations, there's quite a bit of, or their intersubject variability is quite poor. So what that means is, if I was to have my metabolism or VO2 directly measured through a metabolic cart during exercise, and you were, there's going to be quite a bit of difference between the equation, so your predicted, and your actual. And again, remember, we kind of did this before where you look at a predicted number and then see what the actual measured number is. There's typically discrepancy, sometimes a lot, sometimes not much, but some of the error rates observed for these equations can get as high as 7%. So again, if someone's VO2, on a high end, like the highest athletes, will be able to put out 80 milliliters per kilogram per minute. Absolute crazy. They're cross-country skiers. They're phenomenal aerobic athletes. Hands down, probably some of the best in the world. And so 7% of that's like a whole, well, round it up, say 10, that's almost 8. So now you're adding 8 onto 80. That's quite a bit of discrepancy, right? So there's some error there that can crop up in some instances, and we'll talk a little bit about that and when that happens. The other thing is these equations are set and standardized for what's called a steady state. So I think this is the first time we've come across this concept. So steady state is when your system, your body has essentially hit a plateau. So the examples I'm thinking in my head is you start walking up a hill and the hill has a steady gradient and you're walking and you walk at the exact same pace, nothing changes, your heart rate levels out and just stays at the exact same heart rate. Okay, so that's a steady state. Your internal state, the amount of work based off the external load stays the same, 120 beats per minute. And you just stay there, minute after minute, 120 beats per minute. Okay, that's a steady state. Is your physiology ever exactly like that? No, it can be pretty close, but that's the idea behind steady state. Okay. The other component of this is the equations were set up for a sub-max effort. So, for example, when I was using my cross-country skiers example, at their max VO2, that's where some of the accuracy on these equations tend to fall off. And we'll see a little bit more specifically what that looks like on the next slide. And the final kind of assumption, or one of the more larger contributors to these equations, as far as their setup and structure and the assumptions they make, is your RER, which you learned about at last lab, or your fuel consumption, is essentially assumed to be 5 kilocalories per liter. Okay, so, and there's a point on this in your lab, so I won't elaborate too much on this, but in your lab manual, sorry. So it's assumed to be 5 kcals. So why are we using these? There's so many errors. Sean, it's such a specific scenario that these equations are set up on. I hear what you're saying. I hear what you're thinking. And ultimately, it's because it's cost effective. And they are, for the most part, relatively accurate. And especially for their uses in a lab, a clinic, or fitness setting, right? ACSM typically regulates fitness setting largely. So so let's look at all the different equations here that are possible. But on top of that, before we really dive into this chart, again, I know lots of numbers, equations, math, terrible. Let's just take a step back. Okay. Again, remember back to the start of the lecture when I mentioned each of these variables have a meaning. There's a reason behind them. There's a reason they're there. They represent a concept. Okay. It's not just a number. So this is what's going to help you understand conceptually what the equation is trying to help you figure out or understand, which will help you again in turn when you're trying to figure these out in a gym or clinic setting or on an exam when it's asking you a question. Conceptually, you'll be able to figure out maybe a little bit better. So when we're talking, we'll just start with this first column, total metabolic cost. Okay, so we've been over this quite a bit. VO2, volume of oxygen, total metabolic cost, liter per kilogram per minute. That's always the unit. And so what is that saying? Like a lot of students will just tell me, milliliters per kilogram per minute, whatever. But think about those units for a second and what it's really trying to tell you, okay? So for every milliliter of oxygen per body weight, so per kilogram of body weight that you have, per minute of time that passes, that's the exchange happening. So if I have 10, that's 10 milliliters of oxygen. So picture a little 10 milliliter bubble, I guess, of air. So for every kilogram of my body weight, and just for numbers' sake, let's just say 100, every minute, you take that 10 milliliters, times it by 10, or 100, because I'm 100 kilos. So now it's quite a bit per minute. Okay, so 100 of those, like you can see how it adds up really quick to be quite significant amount of volume exchange, even if the numbers are quite small. Okay, so that's total metabolic cost. And again, if you think back to the equation that we keep going back to, food and oxygen, carbon dioxide, heat, water, right? Energy. So we're looking at the volume of oxygen for that reason, because that's the first part of the equation that tells us how much of everything else is going to be occurring, okay? And so again, that's one of the main reasons these are set up. And we don't need a metabolic cart to figure this out now, okay? Because we have these equations. Yay. I know, you're all so excited at home right now, just stoked that this is a thing. Worried last lab, you're like, I won't ever afford a metabolic cart. Why do I need to figure out these concepts? And boom, there you are. Equations delivered for you. Perfect. Great. So metabolic costs, the total metabolic costs. But let's move forward now. So each activity has different parts involved, right? So I'm actually going to jump all the way to the far side here. Look at the resting component, okay? 3.5 milliliters per kilogram per minute. Where have we seen that already? Where have we seen that at rest, our metabolism is 3.5 milliliters per kilogram per minute? METs, right? So MET, same, okay? So if you can kind of keep that in mind, a MET, this is going to help you if you ever have to convert and help you conceptually understand a MET. Again, at rest, 1 MET is 3.5 milliliters per kilogram per minute. Look here, right at the end. What's the resting component that you add on to the other part of the equation to figure out the total metabolic cost of something? 3.5 milliliters per kilogram per minute. Okay, so I have my metabolism accounted for if I was to just be here and resting. Okay, but we're talking about doing physical activity now. So there's some more work, more metabolic expenditure based off of these activities that are going to add to the total metabolic cost. Okay, and what those are is the work. So again, remember that big long chart with the indirect and direct calorimetry and I was going on and on about different boxes of heat and water and air and lighting sugar on fire and stuff. Yeah, that chart. So on that, part of where all that energy was going from ATP was work, right? External work. Okay. And so that's what the last two parts of these equations essentially tell us. Okay. But they break it down into two parts, and that's based off of physics, really. So, when we work in a 3D world and do work on stuff, we essentially have two components that we can do stuff on. So what do I mean by that? So specifically, when we're walking, well, that's the first one we'll go with. So if you're walking on a flat surface, intuitively, if you just think about it, how hard is that relative or compared to walking up a huge incline, like a big hill? I'm trying to think where the biggest hill locally is. For myself, one of the biggest hills would be, I think of the mountain, Cypress, okay? So Cypress Mountain, 12%, 12% incline, pretty much the whole way up on average. That's a lot harder than walking that same distance on a flat ground. Why? Because it demands more work because you're working up against gravity. That's the whole part of the vertical component. Okay, but how are we going to calculate? How are we going to calculate this angle? That's a hard thing to figure out. Like what's going on here? And so, what happens when you have an angle is it gets broken down into two parts. Okay, so the vertical component and the horizontal component. And if you've come across Pythagoras' theorem and different math concepts to do with triangles, and this would make a lot of sense, but ultimately, again, or if you've had physics background, this will be fairly straightforward, but the vertical component and the horizontal add up to be the angular component, okay, as far as distance and work. So, so without getting too much into the physics behind it, at this moment, that's what the last two parts are. How much external work needs to be done to do this activity, okay? So let's go back. We'll take a look at this. So we have our total metabolic cost is what we're looking for. Let's just assume we don't know that right now. So to figure that out, we need to figure out what the horizontal, the flat part of the work is, and the vertical part of the work, okay? And then we'll figure out how much work that is to get from A to B, from down here to up here. And so that's the extra effort on top of our resting component, us at rest, okay? So being at rest plus the work to get from A to B will give us our total metabolic cost, okay? Hopefully that made some sense so far. So let's kind of keep moving forward a little bit in the next steps here. In your lab manual, you're presented with two different equations, one for flat, one for incline walking and running. But ultimately, we can just use the vertical or the incline. And the reason for that is if you're walking on a flat surface, what's the percentage of gradient? 0. There's no gradient. It's flat, right? And so if we look at the math behind that, if we look at the purple here in the vertical component, if my gradient, which is G, or the percentage of gradient, that's on a treadmill, it might say percent, it'll say gradient or grade, and that's what it means, the gradient, which is the percentage or the angle at which you're walking up. So if we put that gradient as 0 here, and the speed doesn't matter here because 0 times anything is 0, right? So I could have 1,000,000 miles per hour here set for speed, right? Or whatever, but I just zero out. So all of this vertical component on a flat just gets zeroed out. So if I'm on flat, vertical component 0, now all I'm left with is my horizontal component, my resting, and that will equal my total metabolic cost, okay? So again, concepts. Resting plus work equals total metabolic. That's the general concepts. Now, just to touch on it, things do get a little more complicated. There's just more variables because of different and or different equipment, right? So walking and running, there's just different speeds really that you're doing those at, and you should notice there's quite a few similarities between the walking and running equations. But you don't have to memorize these; you'll be given them. But you should at least look at the comparison here. Some values are doubled or halved, and again, this just has to do with running. So versus walking. But what I'm trying to get to is the leg cycling. We won't do arm cycling, but I can show you a picture of that later if you're ever curious. You can Google arm ergometer or cycle ergometer, and you'll see what one looks like. But getting back here to the leg cycling. So you notice when we're looking at this, we have a resting component, like in everything. But if you look at the vertical and the horizontal, they look a little different, okay? And so ultimately, and again, these break down into smaller components, these variables, and there's a listing in your manual, but just for here, so S is speed in meters per minute, G is gradient as a percentage, work rate is kilogram meters per minute, and BM is body mass. So so ultimately when you're looking at work rate, it's how much work is being done on the bike, and that can be expressed in a few different ways, watts, etc. But on the horizontal component, you might notice it's still just 3.5, and really it's just because you're seated on a bike while you're going, and the vertical component is the work on the pedals. So that's kind of the only weird one. Again, once we get back to stepping, we see it has a horizontal and a vertical component, okay? So again, take home work plus the rest equals our total metabolic cost, and that's ultimately all they're looking for. Now, just to touch on the limitations, there are certain parameters here and areas, again, that this is ideal for. And again, that's because it's best to have a submax effort and a steady state, okay? And that's what these are really based off of. So this is generally where that aligns to, is these limitations. Now, is that to say if you're trying to predict something for running less than 5 miles per hour, is it still accurate? Well, you can still use it. You just have to be aware that the accuracy might not be as spot on as it would otherwise be. Okay. So again, just some equations, not too, it is math, but it's not terribly overwhelming, especially once you start understanding the concepts behind the math as well. Aside from that, definitely take time to go through the tutorials, work with people, especially people that get it, but even if people don't get it, like your peers, that's fine. Work through these things together, look through the the walkthroughs as far as the answer key, and really try to just come with the understanding that if math isn't your strong suit, that's fine. It's still very manageable, even when it's asking you to look for different variables. If you do get it, I highly suggest you reach out to some peers and offer help. This is only going to help you reinforce that learning and understand it conceptually better for yourself, and have a little bit of fun with it. There's some neat stuff that you get to calculate that's very individualized to yourself for the lab, so that'll be fun. And now you don't need a metabolic cart to figure out energy expenditure, volume of oxygen, and to figure out how to prescribe, say, your work rates for different exercises. Okay. So this week typically has a lot of questions. So depending on what sort of emails and stuff I get, I'll probably set up a tutorial or two But other than that, have fun with it and look forward to the discussions. Okay, take care. Bye.